Hello everyone, welcome back to my channel. In this video, I'm going to talk about topology generated by a collection of sets. Let's get started. We consider set X and a collection B of subsets of X. At this point, we have not considered any topology on X. So our question is, under what conditions on B, there is a topology tau on X such that B is a basis for the topology tau. In answering this question, first we assume that B is a basis for a topology tau. Then what happens is, if we take any U and V in B, then U and V must be open sets. So if we take any X in the intersection of U and V, which is also an open set, there must be some basis element W such that X belongs to W and W is a subset of the intersection of U and V. And because X is an open set, X can be represented as a union of elements of B. So if we take the union of all sets in B, the union must be X. Equivalently, for any X in H, there is some V in B such that B X belongs to V. And it turns out that these two important properties answer our questions. That means if B is a collection of subsets of X that satisfies these two important properties, then there is a topology tau on X such that B is a basis for the topology tau. In order to know more about basis for a topology, please see my video in the link in the description below. Okay, so let's talk about this important theorem. Let X be a set and let B be a collection of subsets of X. Suppose that for every U and V in B and every X in the intersection of U and V, there is W in B such that X belongs to W and W is a subset of U and V, and also for every X in H, there is some V in this collection B such that X belongs to V. Then there is a topology tau on X such that B is a basis for the topology tau. This theorem is very important in a way that it allows us to build a topology on X based on a collection of subsets of X in a way that that collection of sets is a basis for the topology. To prove this theorem, we define the following collection of subsets of X. Tau consists of all subsets of X such that the set can be represented as a union of elements of B, meaning that there is a subcollection B prime of B such that the set is the union of all sets in this subcollection. Based on the first and the second property here, we can show that tau is a topology on X, and by definition, B is a basis for the topology tau. Let's go through some examples in which we use this theorem to show that based on a collection of subsets of X, there is a topology on X such that B is a basis for that topology. In the first example, let X be R and let B be the collection of all open symmetric intervals defined over here. Let's verify that two important properties in the theorem mentioned earlier are satisfied. Take any U and V in this collection. So U is the open interval from minus alpha to alpha, and V is the open interval from minus beta to beta. And take any X in the intersection of U and V. Let gamma be the mean of alpha and beta. Then we can see that X belongs to the open interval from minus gamma to gamma, and that open interval is W. So X belongs to W, and W is a subset of the intersection of U and V. In fact, in this case, W is equal to the intersection of U and V. Okay, so the first property in the theorem is satisfied. The second property is also satisfied because if we take an X in R, X can be contained in some symmetric open interval. For example, let alpha be the absolute value of x plus 1 and let v be this open interval. Then v belongs to B and x belongs to V. Therefore, B is a basis for a topology tau on R. And it is easy to see that tau is this topology. It consists of the empty set, the entire space X, and all symmetric open intervals. In the next example, we consider X equals R again, and let B be the collection of all half open intervals A, B, where A is included and B is excluded. Again, we are going to show that two properties in the theorem are satisfied. Take any U and V in B. This is U. U is the interval from A to B, and V is the interval from C to D. Let and we take any X in the intersection of them. Okay, this is X. Now, let alpha be the maximum of A and C, and let beta be the minimum of B and D. Define W as the interval from alpha to beta. Then X belongs to W, and W is a subset of the intersection of U and V. In fact, W is equal to this intersection. So the first property in the theorem is satisfied. The second property is also satisfied because if we take any X in R, it belongs to some half open interval. For example, let V be the interval from X to X plus 1, then V belongs to B and X belongs to V. Therefore, by the theorem mentioned earlier, B is a basis for a topology tau on R, which is called the lower limit topology on R. The next example, which is also the final example we consider in this video, is rather involved. We consider X as the upper half plane. It consists of all elements x, y in R2 such that the second component is greater than or equal to 0. And then X can be represented of L and P, where L is the x-axis, and also P is the positive upper half plane given over here. Given any A in L and R greater than 0, we define this half ball as follows. UAR is the union of A, this single point set A, and the intersection of the open ball with center at A and radius R with the positive upper half plane. It looks complicated, but we are gonna illustrate this set in the next slide. Okay, so the red figure here represents UAR. It is the union of A, which is this point, and this half ball, excluding everything in the x-axis. Okay, so again, it's the union of A and BAR intersection P. Now, consider the following collection of subsets of X. B consists of all open balls in the positive upper half plane along with all UAR where A is in L and I is greater than 0. So it consists of B consists of all open balls in the positive upper half plane along with all half balls UAR defined earlier. Then we can show that B is a basis for a topology tau on X, which is called the half-disk topology. So we can show that the first property is satisfied based on the following figure. Okay, so if we take any U and V in B and any X in the intersection of them, there are three cases. So if U and V are open balls in the positive upper half plane, then we can find another open ball with center at X and radius R such that that ball is a subset of this intersection. And in the second case where U is an open ball in the upper half plane and V is a half ball UAR. And X here belongs to the intersection of them and X is in the positive upper half plane. Then we can find another open ball W such that this is true. X belongs to W and W is a subset of the intersection of U and V. And in the case where x is a point in the x-axis and it is in the intersection of u and v, then u and v must be a half bond u ar1 and ux r1 and ux r2. By taking the mean of the radius, we can show that there is a set w that is a half bond u ar ux are actually, and w is a subset of the intersection of u and v. The second property of the theorem is also satisfied. Okay, and the proof is quite simple. Okay, now we consider X with a half disk topology in the previous example. Then we can show that the following properties are satisfied. L, which is the x-axis, is closed in X. And for any A in L, for any A in the x-axis, the single point set A is open in L with the subspace topology. Consequently, any subset of L is open in L with a subspace topology. Thus, any subset of L is closed in L with a subspace topology. The fifth property says that any subset of L is closed in X. The sixth property is very interesting. X is T2 but not T3. We are going to sketch the proof of this theorem. How to show that L is closed in X? We take the complement of L in X, which is P, the positive upper half plane, and we can show that it is an open set because if we take any X in the upper half plane, then there is an open bond in the positive upper half plane, and that bond contains X. Remember that each open bond in the upper half plane belongs to B, and therefore it is an open set. So therefore, the positive upper half plane P is an open set. Therefore, L is closed. Now, each single point set A, where A belongs to L, is open in L with the subspace topology because it's the intersection of UAR and L, where UAR is open in X because UAR belongs to B, so it is open in X. Okay, so by the definition of the subspace topology, this single point set is the intersection of an open set in X with L. Therefore, this set is open in L. Okay. So how come this property is satisfied? We can look at this figure here. Okay. So if we take any A in L, it's the intersection of UAR with L. Consequently, for any subset A of L, A is the union of all single point sets in A. So A is open in L. Now, for any subset of L, its complement is open in L by the third property. Therefore, F is closed in L. The fifth property is also satisfied because if we take any subset F of L, by the fourth property, F is closed in L. So by the definition of the subspace topology, F can be represented as the intersection of L and a closed set C in X. And by the first property, L is closed in X. So F is the intersection of L and C, and both of the sets are closed in X. Therefore, F is closed in X. We can show that X is T2 but not T3. In fact, we can take say this set F. F is the interval from -1 and 1 on the x-axis. Okay, so X, for example, is the interval from -1 and 1 on the x-axis here. And let the point A be say 0, no, 1 0. Okay, 1 0, 1 0. Then we can show that we cannot separate F and A by two disjoint open sets in this topological space. We will talk about that in our future video. Okay, so that's it for our video on topology generated by a collection of sets. Thank you for watching.